Hey guys, thank you for checking out this video. If you want to start learning about semiconductor packaging, then you're in the right place. This is Lito Galera and welcome to my Watch, Learn and Play channel. So what is semiconductor packaging? Semiconductor devices are made in wafer form. Each wafer contains hundreds or thousands of devices or silicon chips as we also call it. Semiconductor packaging is actually a series of steps from cutting the wafer into single chips and to transform them into a molded single device that is ready for use to make an electronic system. Semiconductor packaging involves many processes, and this slide shows the basic process flow. Wafer saw is the process of cutting the wafer into individual chips, or commonly called as die. Die attach is the process of mounting or attaching the die to a lead frame. A single device or die has multiple input or output terminals. Wire bond process is a step that connects each die input or output terminals to individual pins or leads of a lead frame. Molding is a typical method of encapsulating the bonded device. Once molded, the device is protected from damage due to handling and also from environment. Marking step adds information about the device and makes the molded device visually identifiable. Plating, trim form singulation, and final tests are the final steps to complete the packaging process. I will discuss in the next slides more details of each process steps. So if you're still interested, just hang in there. Wafer saw is the process of cutting the wafer into individual chips or dies. Wafers are brittle. They break easily if not handled properly. And because each wafer contains many chips, the cost of accidentally damaging or breaking a wafer is quite expensive. In other words, wafer saw process is a delicate step and can be very costly if not done properly. Let's talk a little bit about wafer sizes. Wafer comes in different sizes. Wafer sizes that are in mass production are 4, 5, 6, 8, and 12-inch diameter wafers. 4 and 5-inch wafers are mostly for discrete devices, which are diodes and transistors. Because they are single devices, they are typically small, mostly less than 1 square millimeter in area. With their small size, a 4-inch wafer diameter can hold thousands of diodes or transistors. 6-inch wafers are common for power transistors and low pin count ICs. These are slightly bigger devices, can be up to 3 millimeter in length or width. 8-inch wafers are common for high pin count ICs, and also in some low pin count ICs and power discrete devices for better manufacturing costs. The most expensive wafer is a 12-inch diameter wafer, which is for advanced high pin count ICs. 12-inch wafers also require more advanced equipment as it is more prone to breakage. Let's continue on with the wafer saw process. To prepare the wafer for sawing process, it has to be mounted on a tape. The tape will hold the wafer or dies in place during and after the sawing process is complete. This preparation step is commonly called the wafer mount process. In this step, the tape is attached to a metal ring or a wafer ring, and the wafer is mounted onto the tape. Here is a short video of a wafer mounting process from ULTRON systems. I edited the video a little bit to add titles of sub-steps, but you can watch the unedited full video using the URL provided on this slide. Let's begin. Once the wafer is mounted on the tape, it is now ready for sewing or dicing process. The cut must be done along the sew streets, as center as possible, making sure that the active circuit of the die will not be damaged or chipped during the process. The sewing process is done using a diamond blade. These type of blades are specially made blades for cutting silicon wafers. After the sewing process, the dies are now ready for die attach. Here is a short video of paper sewing process. You can watch the full video using the URL provided on this slide. Let's watch it. Die attach is the process where the die is mounted or attached onto a lead frame or substrate. In most applications, particularly ICs, attachment is done using silver-filled adhesive epoxy. For dies and transistors, it can be a soft solder or eutectic method. Mainly, the selection of the attach method is dependent to device application. In this video, I will focus on using lead frame and epoxy die attach method. This image shows a single unit or cell of a lead frame. Each unit has leads and the attach pad. The adhesive epoxy is dispensed onto the die attach pad, and the die is placed and pressed onto the epoxy to form epoxy fillet on the side of the die. Before we continue discussing the attach process, let's discuss a little bit more about lead frame and substrate. Lead frames are made of copper alloy. Copper is a very good electrical conductor, which is very important material property for electronics application. Likewise, copper is inexpensive. It is cheap. These characteristics of copper makes it ideal in semiconductor packaging application. Lead frames are typically designed in matrix form, which means having multiple rows and columns. This type of design maximizes number of units or cell per lead frame, or what is called lead frame density. The higher the density, the lower cost per unit, which is ideal for manufacturing. Lead frame is suitable for both discrete and IC devices, and for both low and high pin count packages. Laminate substrate is for BGA type packages. It is made of laminated layers of prepreg and copper, allowing high density interconnection for high pin count ICs and high-end advanced packaging. Like lead frame, laminate substrate is also designed in matrix form. Laminate substrate is usually more expensive and cost is dependent on the number of layers it is made of. Let's continue discussing the attach process. A full attach process involves several actions happening all at the same time. This is important to maximize productivity and thus lowering production costs. The process is done using high-tech, high-precision machines. This slide will illustrate the typical process diagram of die attach process. The lead frame loader is the input side of the machine. It is where the stack of lead frame or substrate is placed. The lead frame is picked up from the loader and fed to the work holder system. The work holder system precisely moves or indexes the lead frame from input to output side of the machine, with the timing of movement being controlled by machine software. The adhesive dispenser is located on the input side of the work holder system. Epoxy is dispensed onto the die attach pad every time the lead frame is indexed. The bond station is where the die is placed and typically is on the middle part of the work holder. Wafer handler is where the wafer is held, usually opposite the work holder. Underneath the wafer is the ejector assembly, which pushes the die up so it can be picked up by the pick and place system. The pick and place system or bond arm picks the die from the wafer and place it onto the lead frame die attach pad at the bond station. This cycle repeats continuously, with the lead frame indexing every cycle until all the good dies on the wafer are picked up. Once the lead frame is full, it is then pushed out to the output station, going into an output magazine or carrier. The magazine is unloaded once full. The process starts from left side of the machine, going to the right side of the machine. It is very important that only the known good dies, also called KGD, are picked during the attach process. Otherwise, it will be a waste of material and time processing the bad dies. Let's step back a little bit to explain about KGD, ink dye, and wafer map. Each wafer, after fabrication, undergo electrical testing, also known as wafer sort process. At wafer sort, each die is electrically tested to the device specification. Every die that fails electrical test is inked. Therefore, if you see a wafer with ink dyes, it means that those dyes are bad. A more advanced wafer sort process does not ink the wafer or die, but rather a wafer map is created. A sample of wafer map is shown on the right side of this slide. It is basically consists of ones and zeros, where 1 means good and 0 means bad. Because there's already a wafer map, inking the bad die is not anymore necessary. Here's a short clip of the attach process in action. You can watch the full video using the URL provided on this slide. After the attach process, all materials must be put in the oven to cure the adhesive epoxy. After the attach, and once adhesive epoxy is cured, the die is now ready for wire bonding. Wire bonding is an interconnect process and is a complex process, and it gets more complex as the number of leads or input-output terminals increase. The objective is to connect each die terminal or bond pods to corresponding leads of the lead frame. The bonding cycle is repeated until all bond pads that require connections are bonded. So, for a device that has 64 input-output terminals, the bonding cycle will execute 64 times. Before we talk about bonding cycle, let's discuss the different wire types in wire bonding. Gold wire is the most popular and most commonly used for ball bonding, mainly because gold is a very good conductor and soft, which is suitable for aluminum bond pad. The downside of gold wire is it is very expensive. Copper wire is an alternative material to gold, especially that it is a better conductor. Copper, however, is harder than gold, which makes it tougher to bond, and also oxidizes quickly at high temperature. But gold price started to go up significantly in early 2000, thus the conversion to copper wire was inevitable. Silver wire was also developed for low-cost ball bonding. Silver is also a good conductor, although inferior than gold and copper. It is, however, softer than copper and less prone to oxidation. Aluminum wire is as old and popular as gold wire. It is, however, used for wedge bonding. Because aluminum is cheaper, it can be used in larger diameter. Larger wire diameter can carry higher current. Thus, aluminum wire is mainly used for power semiconductor devices. Let's now discuss the structure of a wire bonded device. On the left side of this slide shows components of a bonded device, which includes the device itself, or what we call die, which sits or attached to the die attach pad. The wires connect the die to the leads. A more detailed illustration is on the right side. The bonded ball is bonded onto the bond pads, and the stitch is bonded onto the lead, and the wire loop that is formed between the bonded ball and the stitch. Let's now discuss the most important topic of wire bonding process, which is the bonding cycle. The cycle starts with capillary on idle starting position with pre-air ball hanging on its tip. The capillary will then start to descend at a controlled speed, and the pre-air ball now securely sitting on the capillary tip. The capillary will continue to descend until it touches down onto the band pad. At touchdown, a controlled bond force is applied through the capillary, which is held by the transducer. The bond force controls how the pre-air ball is pressed or mashed onto the band pad. The ultrasonic power is then applied by the transducer for a certain amount of time, where the scrubbing action of the mash ball to the band pad happens to form the banded ball. At this stage, the first band cycle is complete. After the first band, the capillary will move up to a kink height, which is the start of the wire loop formation. The capillary will then move for a reverse motion, which is to bend the wire in preparation to forming the actual wire loop. After reverse motion, the capillary will then move towards the leads, following a motion set on the loop parameters of the machine. The capillary touches down onto the leads to form the stitch or second bond. The capillary will then move up to break the wire and form a tail on the capillary tip. A high voltage spark will then melt the tail to form a new pre-air ball for the next bond cycle. Let's now watch the actual bonding in slow motion to understand more of the bonding cycle I described in the previous slide. Just like the previous clips, you can watch the full video uh, using the URL provided on this slide. Let's watch. For high volume mass production, it is always desirable to do high speed bonding for maximum productivity to lower manufacturing costs. Let's watch high speed bonding in action in this clip. As usual, you can watch the full video using the URL provided. We have completed three main processes, which are wafer saw, die attach, and wire bonding. If you like the video so far, please don't forget to click the like and subscribe buttons. An exposed bare die is already prone to damage due to handling. An exposed wire bonded die is much more prone to handling damage due to wire being very soft and protruding higher than the die. Also, any movement or flexing of the lead frame will break the bonded wire. In many applications, semiconductor devices are put into extreme environmental conditions. These include very hot temperature, freezing weather, and high humidity. All of these can cause damage to the device. In this regard, the semiconductor device has to be encapsulated or molded after wire bonding. At least the die side or top side needs to be molded. Depending on the package type, the bottom side may be molded as well. The molding material is called epoxy molding compound or EMC and typically in pellet form. Transfer molding is a typical process for molding semiconductor devices. In a transfer molding process, the lead frame is placed on a heated mold cavity and clamped very tightly. The EMC is placed and melted through the transfer pot. The molten EMC flows through the runners and to the cavities, molding individual units of the lead frame. Multiple lead frames are processed in a single mold shot. We are now at the home stretch of the packaging process. After molding, the device is technically unidentifiable. There's really no indication of what device is inside the package. Thus, after molding, the package has to be marked. In the marking process, several important information are printed or engraved on the package. The information include company logo, device code, manufacturing date code, manufacturing location code, and pin 1 orientation. The size and amount of information is dependent or limited to the size of the package. A sample image on the right is an IC device made by Analog Devices. After marking process, the next step is to have the copper lead frame thin plated. Thin plating the copper leads provides resistance to corrosion and also good solderability that is suitable for electronics application. And finally, after tin plating, the package are now ready to be liberated to be an individual devices. Trim, form, and singulation, or TFS, is a series of steps that are done sequentially within the same machine. Trim step removes the tie bars to separate the leads. Form step is the forming of the leads, typically galving form. And finally, singulation step separates and singulates the device from the lead frame. That completes the packaging process. After packaging, the devices are all electrically tested to their specifications. Obviously, only the aesthetically good and electrically good devices are sold in the market. I'll be uploading more videos related to wafer saw, die attach, and wire bond with more process details. Don't forget to like, subscribe, and share my channel and this video. Thank you for watching.